In this video, we're going to be tackling this definite integral, which is I of n comma m, which is the integral from 0 to infinity of sine of x to the power of n divided by x to the power of m dx, where both n and m are real values, where n is greater than m, which is greater than 1. And these are requirements they need to impose in order for convergence. So I've done a couple of videos illustrating different ways of approaching sine of x divided by x and how the integral from 0 to infinity of that gives pi over 2. But I thought it might be just a little bit fun to go through a pretty serious extension of that. And the nice thing about it is that we can apply the exact same reasoning across Method 2 and Method 3 for people that might be interested. If anyone is, please let me know and I'll post up the links to them. Actually, I will have links posted up to the comments if people would like to have a look at it. This can be very easily done with Laplace transforms, which is what we're going to do today. But equally, it's probably easier to use, and I refer to it in Method 3 as R's master theorem, but it's the brilliant Indian mathematician, and I'm very scared I'm going to mispronounce his name here, but Ramanujan's master theorem. So again, I'll have a link to it. It's the Method 3 video if you would like to have a look at it. If you take what we do here, or the approach that we took, in the Method 3 video link that I'm going to put up, and you apply it to this scenario, you'll see that it's actually probably easier to go about it that way than Laplace transforms. Anyway, in order to be able to solve this, I'm going to be taking the same process as what I put up in the Method 2, which is to employ Laplace transforms. And in doing that, we introduce a parameterized function, or we introduce a parameterization, I should say, of the integram that forms a function. So here I'm going to introduce j of t, comma n, comma m, which is equal to the integral from 0 to infinity of sine of t x to the n over x to the m. So you can see here it's obviously very, very similar. The only difference is I've just put a t at the front. Here t is a positive real value, and we observe that this integral here is just this integral evaluated when t is equal to 1. So if I put t is equal to 1 into that, I have 1 by x to the n, which is x to the n, which is just equal to that. So that's what we have here. And that's something that we'll obviously need later on. Okay, so what I'm going to do here is I'm going to take the Laplace transform with respect to t. And in order to do that, I need to appeal to what's known as, well, actually, sorry, my apologies first. Let's just make sure we cover all our bases before we move forward. In order to use this parameterization or this function, we need to appeal to the dominated convergence theorem. So the conditions upon which using the dominated convergence theorem hold in this case, but if you would like to have a more detailed view of it, I recommend looking into that. If anyone has any questions or would like me to go into the detail of why the dominated convergence axioms are satisfied with this integral transformation, please let me know, and I'm more than happy to post up a video to go through that. Now, when we take the Laplace transform, which we're doing here of this function, obviously we're taking it on this side, which means we take it on this side, but we're taking the Laplace transform of an integral. Now, in order to be able to do that, we need to appeal to a theorem known as Fubini's theorem, F-U-B-I-N-I theorem. And so once again, too, there are conditions upon its use, and so they are satisfied within this case, but just as with the dominated convergence theorem, I recommend that you check that out for yourself. If you get stuck with it at any point, or just in general you would like to see a video explaining that, then please let me know. The reason why I've omitted it from this video, as with the dominated convergence, is that I could do a whole video just on that. So I'm just trying to show you that in this case it is satisfied, and so we can just sort of move forward. But by Fubini's theorem being applicable here, that means that when I take the Laplace transform of an integral, it becomes the integral of the Laplace transform, and that's the critical feature here. Now remember, we're doing the Laplace transform with respect to t, so that means that anything with respect to x can just be brought out the front. It's treated as a constant. So I can just bring this 1 over x to the m component here out the front, and I'm taking the Laplace transform of this part of the integram, which is sine of t x to the n. Remember, with respect to t. Now, the Laplace transform of sine of at is equal to a over s squared plus a squared, which means that the Laplace transform of sine of t x to the n, so our a term here is x to the n, becomes a, which is x to the n, over s squared plus a squared, which is x to the n squared, which is x to the 2n. So we now know what this Laplace transform actually achieves. So Laplace transform of j of t, n is equal to this component here, which we already had, which is equal to 1 over x to the n, and then we replace it with the term that we just derived here. X to the n over s squared plus x to the 2n. And so just cleaning it up, I've got an x to the n term here, an x to the n m term here, which is just obviously equal with our indices laws, x to the m minus m. So you remember before, excuse me, that I imposed that n was greater than m. And the reason for that is we need this to be a positive value. If this isn't a positive value, then this integral does not converge. So in case you're wondering why this condition was imposed, it's because of this. We cannot have that as a negative term because that would essentially bring the x term down, and then that would not allow convergence to occur, and therefore for the integral to be resolved. Okay, so this form of integral here, or this structure I should say, is something that I come across a lot, and it has a very simple expression. Well, not a simple expression. It can be derived very simply into a form of the gamma function, which I'm going to do in a video possibly today, but definitely by Sunday latest. So what I'm going to have to ask you to do at this stage is to just trust the result that I'm about to put forward. But again, I strongly recommend that you give it a go yourself. But if not, wait until Sunday afternoon, absolute latest, and I'll also have a video posted up. So if you're watching this just on its own, if you hit the subscribe on Sunday, you'll get the video. Up to you. Okay, so this is the generalized integral that I'm referring to, and it refers to the integral a, comma, n, a, comma, k, comma, n, comma, m, which equals the integral from 0 to infinity of x to the k over x to the power of m plus a all to the power of n dx. Now, one thing I should have written in here is that a has to be positive, k, n, and m also has to be positive, but even furthermore, they have to be greater than 1. Actually, I'm pretty sure m just needs to be positive, but if my memory serves, the k and n have to be greater than 1. Either way, if we impose that these, actually no, m does just have to be positive, and let's just impose in this case that k and m have to be greater than 1. That may be imposing a overly restrictive restriction. It may be that they just have to be positive, but it will just guarantee convergence in this case. Anyway, we see that it takes this form here. A to the power of k plus 1 over n subtract m over n gamma of n times by gamma of m minus k plus 1 over n times by gamma of k plus 1 over n. So this might look a little bit nasty and complicated, but in this situation it's actually beautiful because it isolates out the a term on its own, and that will prove to be very powerful in the next step. So if we apply it to what we have here, we have a very similar integral. X to the power of k, well, our k term here is just equal to n minus m. Our a term here, well, let's start off with our m term. This is s squared plus x to the power of 2n, and essentially this is essentially to the power of 1. So our m term here is equal to 1. Our a term here is equal to s squared, and our n term here is 2n. So this is in the exact same form, and they obviously have the same bounds as well. So this integral here is just, this integral that we have here is just one case of this integral. So the integral that we're dealing with, which is this integral here, is equal to, as we just went through, a is s squared, k, this term here, remember, is equal to n minus m, which is what we have here. Our n term here, so x to the power of n, is x to the power of 2n, so n is equal to 2n in this case. And our m term here is just equal to 1 as we went through, which is what we have here. So all I've done here is I've just substituted in those values into the expression. So a is s squared. Remember, we have k plus 1. K is n minus m, so that's why we have n minus m plus 1 divided by n. Remember, our n is 2n, and then we just have minus m. M is equal to 1, so that's subtract 1. N here again is 2, and I know it's a little bit confusing saying that, but that's just how it is. Gamma of m is equal to 1, so we've got gamma of 1, times by gamma of m minus k plus 1 over n, so that's 1 minus n minus m, k is equal to n minus m, plus 1 over n, which is 2n, times by gamma of k plus 1 over n, which, as we just illustrated there, is gamma of n minus 1 plus 1 over 2n. Now, cleaning this up, we have that this becomes, so if I just push this 2 through here, we have that it's s to the power of n minus 1 plus 1 over 2, because see that 2 there, that just cancels out with that power there. And then pushing that 2 across to this term, it goes from being negative 1 to negative 2. Gamma of 1 is just equal to 1, so we just have divided by 2n here. And then we have gamma of the, gamma of this, well, I'll just say, gamma of 1 minus n plus 1 over 2n times by gamma of n minus n plus 1 over 2n. Now, the beautiful feature about this is that s is isolated out in this individual term. So we have taken the Laplace transform and we just have s to the power of something, and this is effectively a constant. So when I take the inverse Laplace transform in order to be able to resolve j of t, which I then use to resolve I of n comma n, this is so easy because s is just on its own. It's not like I've got s within the gamma function or I've got it involved in some other really complex expression. It's ridiculously simple. It is just s to the power of something, which is so easy to take the inverse Laplace transform on. And so that's why, identifying the patterns and knowing when to use like a Laplace transform or Ramanujan's master theorem or using differentiation under the curve, etc., etc. It does take a while to pick up on the individual patterns, but you start to realize after you do more of these when certain methods work and why they work so well. So the reason why Laplace transform works so incredibly well here is that it transforms this integral here into an expression that we know puts a on its own. And so therefore, taking the inverse Laplace transform, which is the s component, is really easy. Anyway, I'm overexcited because I just find this to be such a magnificent method to apply to this because it's so easy. I mean, this is such a nasty integral, and we're not even solving it for specific cases. We're doing it for any n and m that are real values that satisfy this constraint, which is quite amazing.